far smaller than an atom that winks out of existence in a trillionth of a second. It's evidence of a force that fills all of space, completely invisible, and yet without it, life, Earth, the universe we know, could not exist. Finding this elusive particle marks the end of a quest that required constructing the largest, most complex machine the world has ever seen. A quest that consumed nearly half a century, billions of dollars, and asked thousands of scientists across the globe to invest years, even decades of their careers, with no guarantee of success.
I got a job to do this in 1993.
It's 11th year now.
About 10 years, me.
Yeah, and about 5 years for me.
20 years, something like that.
Since 1994.
It's practically my whole professional life that's led to this point.
The discovery has been hailed as one of the greatest scientific victories of all time and has already won the Nobel Prize.
It's an enormous triumph. This was my generation's Manhattan Project, and I wanted to be on the inside looking out, and it's been extremely exciting.
But what is this mysterious quarry? What does it actually do? And why was finding it so important? That story begins at the very beginning of time, when the universe came into being in a massive explosion called the Big Bang.
So here we have the Big Bang.
Billions of years ago.
Deserves a little bit of color, I think. And then the timeline of the universe. This is where we are. It's now the age of the universe at 13.7 billion years after the Big Bang. And so, working backwards, we had the dinosaurs. So here's a dinosaur. Then life itself, first DNA, was about 4 billion years ago.
Before DNA, there was the Earth. Before that, the first stars. Before them, just atoms. While atoms were once thought to consist of just 3 basic particles, neutrons, protons, and electrons, physicists now know some of these are made of even more fundamental stuff. The basic building blocks of our universe.
The big question then is, where did those building blocks come from? The answer to all that lies in the first second.
In the first instant of existence, when the universe was unimaginably hot, the cosmos was filled with identical bundles of energy moving at the speed of light, all indistinguishable from one another. But then, something changed. Distinct types of particles emerged with different properties, like electric charge and mass. What we experience as weight. Now, we live in a universe full of tangible stuff. And while that monumental shift from nothing to something must have happened almost immediately, how it happened was one of the biggest unanswered questions in physics.
The mysteries of existence lie within this second. Certainly, we understand the science, we understand the physics, up backwards into this second, but at some point we just run out of knowledge. And the Large Hadron Collider is allowing us to see right back to 10 to the minus 12 seconds after the Big Bang. Beyond that, here be dragons, who knows, or dinosaurs.
The Large Hadron Collider is a massive particle accelerator, the largest machine in the world, designed to simulate the universe as it was a trillionth of a second after the Big Bang. To solve the mystery of mass, it smashes protons together at energies so high that it is capable of testing an idea first suggested in 1964 by several scientists around the world. including a young theoretical physicist named Peter Higgs. His mathematics suggested that right after the Big Bang, an invisible energy field was somehow switched on and now fills the entire universe. Just the way that a magnetic field affects some materials but not others, he suggested that this new field selectively affects some fundamental particles, causing some of them to take on mass. Very massive particles, like the quarks that make up protons and neutrons, interact strongly with this field. Electrons, which form the outer shells of atoms, interact less strongly and are very lightweight. And still others, like photons, particles of light, have no mass because they don't interact with the field at all. The theory implied that a universe without a Higgs field might not be a very friendly place, and that got people's attention.
If there were no Higgs mechanism, elementary particles wouldn't have mass.
If electrons didn't have mass, that means they would move at the speed of light. And if electrons move at the speed of light, electrons do not settle down into atoms. And if electrons do not settle down into atoms, there are no molecules, there's no chemistry, there's no life.
Nothing. It would look nothing like what we see today.
We wouldn't be here, and there would be no physicist to ask these questions.
When Higgs submitted his theory to a journal, the editors based at CERN rejected it.
My reaction was they clearly hadn't understood what I was saying.
Undeterred, he revised the paper, adding a paragraph saying, in effect, that if the field exists, we should find evidence of it in the form of a particle that would turn up in an accelerator. In other words, if you smash particles together energetically, you'll make a ripple in the field. And if you apply enough energy, you just might be able to detect it in the form of a particle. The second time around, an American journal published the paper and Peter Higgs got a lot of credit. But in reality, the idea was cooked up independently by a bunch of scientists. Philip Anderson, Robert Brout, Francois Angler, Jerry Guralnick, Carl R. Hagen, Peter Higgs, Tom Kibble, Gerard Etouft. Some have suggested that it really should be called this. But since that's impossible to pronounce, it's simply called the Higgs field. Gradually, the theory gained support. But without the evidence of a particle, now called the Higgs boson, it remained unproven.
To be honest, we weren't sure that the Higgs existed.
Mr. Higgs and his collaborators were saying that there was an invisible energy field everywhere in the universe. So the invisible sounds a little odd, and the everywhere in the universe also sounds kind of far-fetched. So that was a lot for people to swallow.
There are many people who thought this can't be the answer. I've heard people describe it as a trick. You know, it was just a mathematical trick to make the equations work out.
Finding something that's all around us is surprisingly tricky, because the Higgs boson doesn't actually exist, at least not in any form that we can easily detect. So in 1998, scientists from around the world came together at CERN, the Center for European Nuclear Research, located on the border of France and Switzerland, to build a particle accelerator that would have enough power to create such a profound disturbance in the Higgs field that the predicted Higgs bosons would pop into existence and present themselves. But easier said than done.
In order to find this particle, we had to build this complex cutting-edge accelerator.
The work is the work of thousands of people. 20 years of effort went into building these detectors.
20 years of efforts of the international communities.
From dozens of nations, with the US contributing $500 million. It took $10 billion and 10 years to complete the Large Hadron Collider. A massive masterpiece of engineering to find one of the tiniest pieces of the cosmos.
It's a very cool and expensive eye that can look at very, very small distances, like about a billionth of a meter.
We designed this machine so that wherever the Higgs boson would be, we would be able to find it.
Flushing the Higgs out of hiding begins in a modest little red bottle full of hydrogen atoms, the smallest and most abundant element in the universe.
All the protons that we use at CERN are taken from a bottle that size. They start their journey here, and they continue down this orange line, and that is the linear accelerator.
Trillions of hydrogen atoms stripped of their electrons are injected into the collider.
Every 1.2 seconds, 10 to the power 14 protons are being accelerated down that line.
The protons accelerate around larger and larger loops until they are finally directed into the main ring. To keep the increasingly energetic particles confined, the LHC relies on immensely powerful magnetic fields generated by 1,232 primary superconducting magnets, cooled to just a few degrees above absolute zero by 120 tons of liquid helium. After about 20 minutes of acceleration, each bunch of protons is moving at nearly the speed of light, with as much energy as an onrushing locomotive. Finally, the protons are carefully steered into violent head-on collisions, converting the huge energy into showers of exotic, energetic particles scattering in all directions, many decaying into showers of even more particles, setting the stage for the hard work of detecting the Higgs.
Trying to figure out what happens in the collision of two protons at very high energy is like analyzing what happens in the high-speed collision of two garbage trucks. Garbage is spread all over everything, and most of it is garbage in the sense that it's not interesting. It's old stuff that we already knew about. And in all this garbage that's spraying out in all directions on the highway, you have to find the golden needle, the rare artifact that you're looking for, the Higgs boson, something entirely new.
To the scientists at CERN, a collection of physicists from all over the world, the stuff produced in these powerful collisions is anything but garbage. Each particle has a well-understood identity, described with great precision in one of the most accurate theories ever devised to explain the workings of the universe. It's called the Standard Model, and one of its key contributors is Frank Wilczek.
Hi, welcome. Come on in. A lot of what I do is really just play. I mean, I play with the equations and ideas.
All that playing won Frank a Nobel Prize for his contribution to the Standard Model.
Well, what have we got here? Looks like an instrument of torture for the mind.
The Standard Model is essentially an understanding of how all the known pieces of the universe fit together, except for the mechanism of gravity, creating a mind-boggling tapestry.
This is going to be a hell of a puzzle to figure out. All right, now we've had a promising start. We think the Standard Model contains all you need, in principle, to describe how molecules behave, all of chemistry, how stars work, all of astrophysics. Not only how things behave, but what can exist. These are the rules of the game. The ingredients of the Standard Model are of three basic sorts. There's what you might broadly call matter. That's sort of lumps of stuff that have a certain degree of permanence. And these are, on the one hand, quarks. They include the building blocks of protons and neutrons and atomic nuclei. And leptons, most prominent lepton in everyday life is certainly the electron. So those are matter particles. On the other side, we have what you might call force particles or force mediators.
Called bosons, some of these particles are more like lumps of energy. They transmit the forces that bring the matter particles to life. They include the photon, which carries the electromagnetic force, the gluons that carry the strong force, which holds protons and neutrons together, and the W and Z bosons that are responsible for the weak force governing radioactivity. With just this small list of ingredients, the Standard Model explains the physical properties of the elementary building blocks of nature.
The Standard Model is just a handful of particles and forces, and it explains every experiment ever done by every human being in the history of science. So it's quite impressive in what it's managed to do.
It explains how stars burn, it explains how radioactivity occurs, it explains how chemistry works, it explains how light works. It's an amazing theory.
The first particles were discovered in experiments and became the foundation for the Standard Model. But then the theorists took over, and all the particles discovered in the last 40 years were first predicted by the mathematics of the Standard Model and then found experimentally. The Higgs boson, a force particle, was the last and most challenging piece of the puzzle. That's why finding it was such an obsession among theorists and experimentalists alike. In September 2008, with much fanfare,
Yes, sir. Yes.
the giant accelerator was switched on.
So you can see the beams oscillating.
The LHC was ready to go to work. It was an exciting time, full of high expectations.
Designing and building this machine, it is just incredible to see it come to life.
But then, just 9 days after startup, disaster struck.
It was 11 o'clock in the morning, and I got a call to come over. Something looked serious, and when I got over there, I have never seen such carnage.
A short circuit burned a hole in a giant container of liquid helium used to cool the magnets. 6 tons of helium was released into the tunnel, and more than 50 of the giant magnets were fried. The $10 billion LHC was dead in the water. Undaunted, engineers worked to repair the machine, and physicists continued to refine the computer programs that would analyze the vast amount of data that the LHC would produce once it was running at full power.
3, 2, 1.
By late 2009, after 14 months of repair work and re-engineering, the LHC was more robust than ever, and finally ready to begin the hunt in earnest. Now, protons are whizzing both ways around the ring at nearly the speed of light. At the center of the 2 Higgs detectors, the beams cross. Inside Atlas, a massive machine the size of a cathedral. And also within its smaller cousin, CMS. Even though the beams are microscopically small, the vast majority of particles contained in them whiz past each other without incident.
When you collide 100 billion protons and 100 billion protons, most of the protons are just seeing each other and going, hello, and going on.
But about 800 million times every second, pairs of protons meet head-on.
What's called a hard collision. When the proton breaks up, so it's no longer a proton, that's an interesting collision. And that happens only about 20 times out of all these billions of protons crossing.
In each of these powerful collisions, dozens of new particles flash into existence and spray outward. Their unique signatures tracked by the huge detectors, capturing the action 40 million times a second. Incredibly fast, but still not able to spot the Higgs directly.
Higgs is actually kind of a difficult particle to find. It's kind of subtle in how you look for it. As soon as you create it, it decays very, very quickly. The lifetime of a Higgs is about 1 zeptosecond, which is like 10 to the minus 21 seconds. So in fact, you'll never even see it in a particle accelerator. It doesn't move that far enough for you to see any track left behind.
And so, the only way to detect the Higgs would be by spotting the more familiar particles that the quickly vanishing Higgs decays into. The math predicted about a dozen different possible decay modes, as they're called. But the relative likelihood of any of them depended on the mass of the Higgs, which was a total mystery. It must have seemed like a cosmic joke on the theorists.
The irony, if you like, is that although the Higgs field that's related to the Higgs boson gives other particles mass, the one property of the Higgs boson that was not predicted by Professor Higgs and his colleagues was the mass of the Higgs boson itself. So its mass could have been anything from very, very light by our standards to very, very heavy.
Since the Higgs could theoretically decay in so many different ways, the Higgs hunters had to be willing to sift through all of the collision debris, looking for slight increases in the number of detectable particles with very specific characteristics into which the Higgs could possibly decay.
So it's not like looking for a needle in a haystack, when at least you know that you found a needle. It's like looking for hay in a haystack. You're looking for a little bit more hay with certain properties than certain other properties.
That daunting challenge meant building enormously complicated detectors to track and count every bit of debris coming out of those collisions.
And then we have to somehow, with all the particles that come out of this event, we have to reconstruct them and find if there are new particles that are happening.
The mathematics predicts that the Higgs should often decay into particles that are also maddeningly hard to detect, like quarks, the particles that make up protons and neutrons in the nuclei of atoms.
They looked in every possible way they can look. In the end, they looked for the Higgs boson decay into photons.
Out of every 1,000 Higgs bosons created, a few should decay in a way that produces a pair of photons, light particles, which can be measured very precisely in the detectors. By knowing the energy and angle between pairs of photons, scientists can tell if they were likely produced by a Higgs. And by looking for unexpectedly high concentrations of certain photons over billions of collisions, scientists hope to zero in on the Higgs and, as a consequence, pinpoint its exact mass, the one missing value in the theory. It proved to be a statistical sifting process of dizzying complexity. Luckily, they had a head start. Years of experiments in other colliders had ruled out many possible masses for the Higgs, measured in units called giga-electron volts, or GeV.
So on this line of what the mass of the Higgs might be, we can draw on what previous experiments have tried and where they've been able to exclude it from being.
A less powerful accelerator, the LEP Collider at CERN, a predecessor of the LHC, had already ruled out the Higgs being at the bottom end of potential masses.
In fact, they were able to say that the mass of the Higgs is, with 95% confidence, 114 GeV or more. So after LEP, the next major milestone in the Higgs search was limits set by another collider in the US, the Tevatron. The Tevatron was able to exclude a range here around 160 GeV here.
In 2011, CERN moved that upper boundary still lower.
The LHC has been able to rule out a big region from 145 quite far up.
But this last remaining energy range was also the trickiest to search. It's the area in which the unique signature of the Higgs would be most deeply buried under the background noise of other particles created in the collider.
If I was to bet, I would probably put it at 130 GeV.
Probably somewhere around 120 GeV.
Somewhere between 120 and 130 GeV. 114 GeV. Because it's the most difficult place to look, and we haven't found it yet.
That's a good question, because you're assuming that the Higgs actually exists, which I'm starting to believe it probably does not exist.
As data piled up at the LHC, scientists narrowed the range even further. It seemed that they were either about to close in on the Higgs particle or prove that it didn't exist at all.
People were beginning to worry a little bit that we hadn't found the Higgs yet and maybe weren't going to find it. And that would have been a complete shock because we know that something is doing the job of the Higgs.
Well, you start to get a little nervous because either it's there or there isn't a Higgs boson at all.
By the end of 2011, the window narrowed even further.
The LHC, with the new data from the whole of 2011, is able to expand the area that it can exclude the Higgs from.
The new lower limit had risen to 115 GeV, and the new upper limit dropped to 127 GeV. And within that range, interesting things were showing up in the data.
So the really exciting thing was that the reason the LHC experiments weren't able to exclude anything inside this remaining window is that, in fact, they see an excess of events, the early signs of the Higgs boson, if it's there.
An excess of events means that the LHC was producing more particles of interest, in particular, pairs of photons.
So what you're looking for is called a bump, because at that particular energy, you should see a lot more decays if there is a Higgs boson. So if you see a bump, that's a clue that something's going on.
Those excess photon pairs were showing up in not just one, but in both detectors, and at practically the same mass. CMS was seeing a spike in the number of photons, which could be the signal of a Higgs with a mass of 124 GeV. And Atlas was seeing a similar spike near 125. Now, with the hunt finally closing in, the LHC continued smashing protons, sorting through the debris, and piling up the data for another 6 months.
We saw a signal growing. Every week, every day.
Until at last, on July 4th, 2012, the heads of Atlas and CMS, Fabiola Giannotti and Joanne Candela, called a meeting.
Because we hear two presentations from the two experiments, Atlas and CMS.
There to hear the news firsthand, Peter Higgs himself. It was standing room only.
Good afternoon, everybody in Melbourne.
But it was also beamed live around the world.
Okay.
So, of course, everyone's heard lots of rumors at this point within the collaborations, but there are these two collaborations, the CMS collaboration and the Atlas collaboration, and we aren't supposed to know what they have, and I didn't. You know, you'd heard stories, but I hadn't seen their data. So that's kind of exciting.
So, today is a special day on a search for a certain particle.
But no one was quite prepared for the short, definitive announcement that was to come.
I asked Joanne Candela from CMS to take the floor.
This was about to become one of the defining moments in the history of physics and science.
The energy was so incredible. It was like a big party. People were really excited, And it was just then, I think, I started to really appreciate where we were and that this was a major discovery.
And this slide shows you one event taken just a few weeks ago.
I put the slide up, and before I could say anything, there was a gasp across the whole audience. Now, a major result like this from one experiment could still be wrong.
Now we go immediately to Atlas Fabiola Gianotti, please.
Thank you.
But Fabiola brought the same confidence for her results.
So you can already see here the compatibility between what you observe. One big spike here, in this region here.
If you look at these plots that were shown, first thing you want to see is did CMS and Atlas find the bump in the same place?
And in fact, they had.
In excess at a mass of 126.5 GeV.
Both teams had found an excess of photons pointing to the same mass.
And that was pretty convincing. So you're going, wow, like, we rock.
As a layman, I would now say, I think we have it. You agree? Yeah. We have a discovery.
The LHC had found the Higgs particle.
We have observed a new particle consistent with a Higgs boson.
It's like running a marathon and suddenly realize you crossed the finish line.
Maybe one more round of applause to all the guys supported the whole project for more than 25 years here.
It comes as a big surprise to me, I must say. I went into that seminar expecting good result, but I was gobsmacked, as they say.
The hunt that spanned half a century was over.
The Higgs boson hid for 50 years, but you know, like they said with the Canadian Mounties, they'll get their man. It could run, but it couldn't hide forever.
It appeared Higgs and his colleagues had been right. The mystery of how particles gain mass had been solved. The last piece of the Standard Model had been found.
For me, it's really an incredible thing that has happened in my lifetime.
I had the pleasure to meet Peter Higgs at the end of the seminar and exchange a hug. He told me, congratulations to you and your experiment for this incredible achievement. And of course I replied, congratulations to you. You are the first person to be congratulated.
I think it's not appropriate for me to answer any detailed questions at this stage. This is an occasion celebrating an experimental achievement, and I simply congratulate the people involved.
Ironically, the achievement took place at the very same institute where, nearly 50 years earlier, an editor had rejected Higgs' initial paper.
The Royal Swedish Academy of Sciences.
In a fitting end to the saga, Peter Higgs and Belgian physicist Francois Englert, who had independently come up with the idea for the Higgs field, won the 2013 Nobel Prize. Englert's colleague, Robert Brout, certainly would have been honored as well had he lived to see the day. So why is all this important? Why does proving the existence of the Higgs field matter? Building an enormous Big Bang machine to recreate conditions in the universe near the beginning of time and completing the Standard Model is a tremendous scientific achievement.
Finding the Higgs sheds light on all of particle physics and cosmology. It's all connected. All our models of how the universe began, how it expanded, everything is, affected by the Higgs field and by how we understand the universe.
Perhaps discovering the Higgs boson and the field it proves will open new doors.
The discovery of the Higgs is just the first step. In science, you make a step forward, you answer a question, but then other questions open up.
Into even greater mysteries that still remain beyond the Standard Model.
The Standard Model can't be the final thing. There is something beyond the Standard Model, we know that. Hopefully the Higgs can give us some guidance in that direction.
Yes, we do know the Standard Model works. It works incredibly well. But we know it's not the whole story. And any time in the history of physics where people thought they had the whole story, they were wrong. And so we're looking for what is the next piece, not just in terms of one particle, but in terms of forces, in terms of understanding nature.
The number of mysteries in the Standard Model is huge, which is fine because as a scientist, I'm drawn to mysteries.
One mystery that the Standard Model can't answer is perhaps the most fundamental of them all. Why isn't our universe empty? Because according to the mathematics behind the Standard Model, it should be.
Science has given us a set of laws that describe the world so accurately that we can predict the motion of a coin tossed in the air because we understand the law of gravity. We understand electromagnetism so well that we can use our GPS satellites to locate your car to within a few inches. And we understand the nuclear force so well that we can predict the future evolution of the sun itself.
Those mathematical equations that work so well to describe the laws of the physical world are bound together by something that we see around us every day. Something that characterizes our faces and the natural world. Even the tiniest structures, like viruses, and our DNA, symmetry.
In the Standard Model symmetry rules, the laws are dictated, really, in their form by requiring tremendous amounts of symmetry. That's how we found them.
The equations of the Standard Model seem to predict a universe in perfect balance, formless and without structure, as it was at the very beginning. And if it had remained that way, nothing would exist.
If the laws of science are framed in their most perfect, most symmetrical form, then life cannot exist at all. There'd be no mountains, rivers, valleys, no DNA, no people, nothing.
A universe created along absolutely symmetric principles would be in perfect balance. The Higgs field is the first clue to what broke the symmetry of that completely uniform early universe.
The state of perfect symmetry is very similar to the state of perfect balance. Think of a spinning top. It exists in a state of perfect rotational symmetry. No matter how you rotate, everything looks the same.
Even more so than the symmetry of a spinning top. At this instant of creation, every place in the universe would have been symmetrical, identical to every other place. But perfection isn't stable.
The slightest imperfection, the slightest little defect will cause it to vibrate, perturb, and fall to a lower energy state. Symmetry has been broken.
Within a fraction of a second of the Big Bang, physicists believe the absolute symmetry of the universe was shattered by a tiny fluctuation. The Higgs field appeared in all of space. The forces split apart. The particles of the Standard Model became distinct. Structure emerged. This fall from perfection was what allowed us to come into being.
Everything we see around us is nothing but fragments of this original perfection. Whenever you see a beautiful snowflake, a beautiful crystal, or even the symmetry of stars in the universe, that's a fragment. That's a piece of the original symmetry at the beginning of time.
Finding and studying the Higgs is a vital first step in the quest to understand that early state. When the particles that make up what we can perceive came into being, as well as a much greater quantity of mysterious stuff that we know is out there, but that we can't directly detect, called dark matter. What are these missing pieces? When James Gates came to study at MIT, he was determined to unlock the secrets of the early universe and understand what happened to the unity that was once there.
We and the universe are intricately tied together. This idea of unity turns out to be one of the most powerful driving themes in physics, and it keeps getting us to look for deeper and deeper connections. So ultimately, perhaps we exist because the universe had no other choice.
He looked at the Standard Model, the matter particles and the bosons, the force particles that hold everything together. He wondered if these two groups of particles that seem so different could be related in some profound and hidden way. This question, why is there a fundamental asymmetry of forces and matter, led him to a powerful mathematical theory called supersymmetry.
It was the asking of this what-if question that drove the construction of supersymmetry, which had an incredible resonance for me when I was a graduate student. I saw one more beautiful balance that we could put in nature.
One of the pioneers of supersymmetry, Jim Gates saw in the mathematics a possible hidden world of new particles no one had suspected.
Mathematics leads us to find things we didn't know were there before. Supersymmetry is an example of that. We know about ordinary matter. The math leads you to discover supermatter and superenergy.
The theory gives every matter particle a force partner and every force particle a matter partner. These heavier supersymmetric twins are labeled sparticles.
So once you believe this math that says there's more to existence, then you have to wonder what these other things are. So you have to name them at a at the very first step. So in nature, there's this thing called the electron. The math says it has a super partner called the selectron. Muon, there'd have to be a smuon. Photon, there'd have to be a photino. Quark, there'd have to be squarks. Z particle, there'd have to be xeno. The W particle, there'd have to be a wino, and that's how supersymmetry works.
According to supersymmetry, matter and forces aren't so distinct after all. There's a grand symmetry between them, but we can currently see only one partner from each pair. However strange it seems, this theory has gained widespread support from theoretical physicists. Not just for the beauty of its equations, but for what it might help explain.
When supersymmetry began as a topic of discussion, no one realized what it can do. It turns out that studying the mathematics, we get a firm foundation for the existence of everything.
Supersymmetry could shed light on dark matter, the missing particles that aren't included in the Standard Model, and even help to explain how symmetry was broken in the first place.
I very much want supersymmetry because it's a beautiful thing by any standard and would take our understanding of nature to a new level. So I want that.
Finding the Higgs pushed the LHC to the limit of what it could do. So, a few months after the Higgs announcement, the scientists at CERN shut down the giant collider and began a planned 2-year upgrade. As it begins its second act, it will smash protons even more energetically.
So when the LHC turns back on in 2015, we will be at twice the energy we were before.
The increased power will help physicists to study the Higgs with more precision. But the real hope is that they will find something entirely new.
Every single experimentalist is only thinking this. Is there a massive particle we can now make with this energy, with these energetic protons that we haven't seen before?
For the theorists, too, it is an exciting and nerve-wracking time.
If we find supersymmetry in experiments, for me personally, it will mean that I have not wasted my entire research career, because this is the one question as a young scientist I decided had my name on it to study.
I'm starting to get nervous. You know, so there were a lot of people who predicted that supersymmetry was just around the corner or something else, that as soon as LHC turned on, they'd see spectacular effects on the one hand, or that the Higgs particle would be heavy on the other hand. Those are all wrong. Now it's make or break time.
For the thousands of scientists who have come together in this great quest, pushing the frontiers of knowledge has been a wild roller coaster ride. And with the Large Hadron Collider,
3, 2, 1, 0.
the